Today we talk about infinite series. And infinite series is very mysterious. A lot of infinite controversy is coming from this infinite series. There are several famous ones. Maybe I can introduce that later. But let's look at infinite series, see what we can say about strange nature of this infinite. Okay. Before we get into this, please subscribe if you like and continue receiving the updated subject of the calculus. This calculus is easy. This series, actually, this is 8th subject. Okay. Now we look at power function. And what is power function? C1 x minus a plus C2 x minus a square plus ck x minus a to the case. So question is why we look at this. Okay, textbook doesn't tell you why, and teacher said just trust me and listen. Okay, so let's just listen. There are some intention hidden, and you'll be manipulated here in a smoke, and you get into this world of strange nature of infinity. This kind of function is called a power function because it's all square third and case terms, right? And in order to see what this coefficient is, what we do is we put x equals 0. So f0 equals c0, right? Because all remaining becomes 0. And we take a derivative first, right? Then put x equals x equal a. I'm sorry, a. Okay. After take a derivative, this disappear, and this becomes c1 only, and still have this term. So if you put x equal a, everything disappear. So it's going to be a c1. The next one, don't forget when you take a derivative, this number come down. So the f double prime a equals 2 c2. And here x 3 times derivatives a equals 2 and 3 c3. So c3 is going to be f3a, right? And c2 is going to be f2 derivative twice and plug in a 2, so and so. So you can tell fx is going to be like k equals 0, f the times of delivery a, and if you take a derivative 3 times, so it's going to be k f k and x minus a k, right? And k to the n. Okay, so n can be arbitrarily large. It doesn't matter how large n is. Let me clean up here a little with the eraser here. Okay, so now this series has a name, Taylor series. And when x equals 0, you call Maclaurin series. It's strange, huh? It's just you give a is 0 and Maclaurin. Either way, it's fine. Okay. This is like a shifted function. The function shifted by a. If a is 0, there's no shift. So it's going to be like 0n derivative k times 0 x. Let's see. Let me write a little bit neater here. Draw x k. Okay. And as I said, n can be any large number. So power function, if you take a derivative multiple times, eventually it becomes 0. So nothing happened. But function like this, you take a derivative, it doesn't make much difference. Just keep going, right? So here's a potential. By allowing n is infinity, we can express those functions using power function. You got that? The connection here? When n equals infinity, it can be, this kind of function can be equivalent to power function x to the something. That's interesting, isn't it? But does it work? So these are, if you give x some value, it's a finite value. This one, x you give larger x, it's going to diverge to the infinity. Is that so? Well, pay attention to this. When k become larger and larger, this get really large. Any number is divided by this large number. So there is a potential, the fk, this can be finite. Then potential, this going to be smaller and smaller, and even n equals infinity, summation may be infinity, converge. Okay, so how do you know it's diverge or converge? Well, there is a several theorem about how to test series, infinite series diverge or converge. Okay, and this is a very messy area, and nobody remember what's going on. One thing for sure, see, if you have a let's see, you need to have limit here, right? And n equals infinity. A0 plus A1 x plus A2 x square plus A3 x third plus so and so is going infinity, and depends on a, right? So each term you say, including a, say this is the term u2, u3, and uk, and u infinity, you can tell if U3, this ratio is more than 1. Definitely this diverge, right? The even 1, it's going to diverge because you are not getting smaller, and you add infinite number of something not getting smaller, it's going to diverge. So it's that diverge. This condition is satisfactory condition. Okay, how about this get smaller? What's happened? Converge? Well, actually, we do not know. Okay, so we have a little bit more refined testing condition. Now, when you say UK plus 1 and UK, when you talk about this ratio, this is P. But you have to talk about ratio when K is infinity, right? Because in the beginning, it was okay, but later, it's exceed 1, it's gonna diverge. So when K is infinitely large, what is the ratio? This is more important condition. Okay? And turned out this P is less than 1, it's converge. Okay. If P is larger than 1 or equal to 1, wait a minute, equal to 1, don't rush the conclusion. If larger than 1, infinitely going, the term getting bigger and bigger, this definitely diverge. And this one, you need a proof, right? And again, P equals 1, we do not know. So those are sufficient conditions. It's sufficient to say if P is less than 1, it's converge. If P is larger than 1, diverge. P is equal 1, we don't know. Okay. That's important things. And there are many tests. Mathematicians develop many tests, like alternating series. How is the alternating series? It's easier because every time, okay, like S equals 1 minus plus 1 minus so and so. Okay, and this one converge. Why is that? In alternating series, when the term UK is getting smaller and smaller, and limit K is infinity goes to 0, then it's converge. This sufficient condition. The condition, if converge, then what happens if you add up this one, all the plus first, plus term say a plus term, and you have a b minus term. You add all the minus. Does it converge? Can you change the order of adding? Can you change order of adding? Many funny things happen. Some series, if you change the order, it's supposed to be converging become diverge, or diverging become converge, and so on. So can we change the order of adding? It's turned out if a series converges, then okay to change order. This we need proof to. Unfortunately, those proof is quite complicated and take time, so every proof like this one, we spend the time here, YouTube video become too long and everybody go sleep, so we don't try to prove this. Just let you know what you have to remember is actually there are a lot of sufficient condition. Do you remember? Sufficient condition. If A, yes, it's going to be B. And no matter how many you put together sufficient conditions, it doesn't become excuse me, necessary condition. And there are necessary conditions. You put so many necessary conditions, but you cannot say, yeah, this satisfies this necessary condition, necessary 100 necessary condition, okay? But A cannot be B, we don't know. What we need is necessary sufficient condition, or sufficient necessary condition. Bingo. With this condition, you can tell perfect way to test infinite series is going to converge or diverge. Okay, so we don't have this for infinite series. I never seen the one. You look at math book, look for it. I'm not a mathematician actually, not a math major. So actually I never seen necessary sufficient condition for infinite series diverging or converging. That's why this makes very messy. The mathematician list up a lot of necessary conditions, a lot of sufficient conditions, whichever it goes, converge, diverge, but there's no necessary sufficient condition. That's why this infinite series is a monster in the calculus learning. Okay, but it's convenient. For example, if fx equals, let's see, 0 is 1. It's promising. The 1 and plus x squared plus x third x fourth, so and so. Wow, exponential function is equivalent to power function infinite series. What's good about that? Well, you know this getting smaller and smaller. So if you calculate what is the value of e to the 1.1, how do you calculate it? You plug in 1.1 and keep adding. You add about 1 million digit using computer. You get a pretty good approximation of this value, probably 2.7 some whatever, right? So this is good for numerical analysis. That's the only benefit. It's sad if it's a numerical calculation only. Well, we never let it go. Once you came in to this door, we are going to exploit it. And what's happened? Wow, you put imaginary number here. So it's going to be I x and negative. It's going to be x squared positive negative positive. So it's become, oh, don't forget I. It's going to be alternate series, and you put together 1 minus x squared you put all the real part and imaginary part together, right? Oh, this no. Plus negative and this is negative and positive, so it's become x4 x6 minus 6, so this is going to be I together, so it's 1, the x minus plus x5 minus 7, so. Okay, so you see this one? This is even function, and this is what? Odd function. You remember this is going to be cos x plus I sine x. This is exactly what it is, cos x plus I sine x. So sine x is going to be this, and the cosine x is going to be this. Now we cover exponential on cosine, and you know, you can do log and tangent, whatever the function is. Just find the infinite series, and since they converge, you can add two converging infinite series one by one. Okay, you can do a lot of way to massage it, so it's become suddenly fun to exploit this infinite series. Okay, so That's about all I talk about infinite series here in this YouTube. Hope you get idea where these things come from, and it's comforting to know nobody has a neat, sufficient, necessary condition to say this infinite series diverge or converge and stuff. There are messy list of all the necessary conditions, sufficient conditions and stuff. So it's good to know that, right? And nobody tell you this in the calculus class. They just tell you, oh, if this condition meet, it's converge. Yeah, so what? You know, if this condition meet, if this condition doesn't meet, it's diverge. No, we don't know, right? So that's why a lot of unknown associated with infinite series in the calculus, you don't feel comfortable. That's the reason. There's no clean-cut theory about diverging and converging, and using that you can create a lot of fallacy and some strange story, and people will fall into that. And that's the kind of things maybe I can talk about it in a different video. Okay, don't forget to subscribe if you like this video. Thank you for listening.